Moving on to polynomial functions and their graphs. Got a few terms I want to go over before we delve too deep into polynomials. Polynomials have kind of the smoothest graphs out there. Here are some rough examples of some polynomials of the first few degrees. You kind of think of lines, parabolas, anything that has sort of a twisty roller coaster shape to it. Those are examples of some polynomial type graphs. A polynomial, you can represent it in term-by-term form. These are examples of some sort of standard form polynomials that are written in terms of their degree and then in decreasing order by the exponents. So here's a polynomial 4x squared minus 4x minus 15. That's also a quadratic. Anything that's in this form that has powers of x raised to exponents with coefficients involving addition and subtraction, that's what a polynomial calculation is involving. So every linear function is a polynomial. Every quadratic function is a polynomial. Here's an example, negative 6x to the fifth plus 23x to the fourth plus 5x to the third minus 4x squared. Writing everything in descending order by the powers of x is a relatively standard way to represent a polynomial's graph or polynomial's equation. Now, you can represent a polynomial in these forms for their equation, but in the rare event that they can be factored, you can also represent them in a factored form. So this polynomial f of x can be factored this way as two binomials. This polynomial named g of x can be factored as a monomial and then three binomials. So sometimes a factored form is kind of handy, especially for finding x-intercepts, because every factor that contains an x would tell you an x-intercept when you set the y variable equal to 0 and try to isolate those intercepts. So some properties that are unique to polynomial functions. Polynomial functions format contains a variable x that's only raised to positive whole number exponents. So you should never see any square root symbols or negative exponents on the powers of x in a polynomial. Polynomials are characterized or they're identified by their degree. The degree of a polynomial is the highest exponent that you see on the x variable. So now keep in mind, the only place you can really get the degree is from this form up here, when it's written in this sort of descending power form. So this is an example of a polynomial of degree 2. All quadratic functions are polynomials of degree 2. This is an example of a polynomial of degree 5. The highest power of x you see there is 5. So that's their respective degrees. Now, since the calculations in a polynomial only involve, raising real numbers to exponents, and then multiplying by coefficients, and then adding and subtracting some terms, then the domain of all your inputs, the x values that can be plugged into a polynomial, are all real numbers. There are no restrictions on the domain of a polynomial function. You can plug any real number into a polynomial's equation to get its outputs. Okay. Now, talking about the graph attributes of polynomials. Polynomial graphs are going to be smooth, connected graphs without any kind of breaks or gaps or any sort of disconnect in the graph. So you'll always be able to graph a polynomial function from left to right without any kind of breaks or skips or jumps in its graph. Now, one thing that might be new to you, see, here's some examples of polynomials based on their degree. If you have a degree of 0, that's technically a constant function. Okay, a polynomial of degree 0 is just a horizontal line. A polynomial of degree 1 is linear. So, any linear function is also a polynomial. It's always going to have a straight line graph. A polynomial of degree 2 is quadratic. That's the quadratic parabola functions we talked about recently. Now, moving higher, a degree 3 polynomial is referred to as a cubic. Now, you don't really have to know that it's called a cubic, but it's pretty intuitive to call it a cubic because its degree is 3. The highest power of x would be 3. Degree 4 polynomial would be called quartic, a degree 5 quintic, but again, you don't have to really commit those to memory. But what I wanted to illustrate to you is notice as the degree goes up, notice how the number of turning points change. If you have a degree 2 polynomial, you'll always have one turning point on a degree 2 polynomial. A degree 3 polynomial can have at most 2 turning points for a maximum and then a minimum. 2 turning points right there. A degree 4 can have at most 1, 2, 3 turning points representing maxes and mins. So in general, a polynomial's graph can always have at most one fewer turning points than its degree. So a polynomial of degree 5 can have at most 1, 2, 3, 4 turning points. Now it may not have all 4 of them, but if it has all the turning points it could, it's going to be one fewer than what its actual degree is. Okay, so that's one thing to keep in mind as you're building toward a better knowledge of polynomial graphs. Okay, now the first major graph attribute that I want to discuss with you is referring to the end behavior of the graphs. In other words, as you go to the far left and right ends of a polynomial graph, sometimes the ends go in the same direction. Maybe both go to positive infinity or both ends go to negative infinity. But there are times where the opposite ends of the graph may go to opposite ends of the y values. The left end may go to minus infinity, the right end may go to positive infinity, or vice versa, like on this one. So it's based on knowing two things. The end behavior of a polynomial depends on the degree of the polynomial, so that's the highest power of x, and it depends on the sign of the leading coefficient. The leading coefficient is the value that's paired with the highest power of x. So here this is a leading coefficient of 4 for a degree 2 polynomial. This is a leading coefficient of -6 for a degree 5 polynomial. So in general, the way this leading coefficient test is used to give you information about the end behavior of a polynomial's graph is this. If you have a positive lead coefficient on an even degree polynomial, the left and right ends are going to go upward like this. So here's an example of an even degree that has a positive lead coefficient. The left and right ends go to positive infinity, like that illustrates. Now notice, there's a deliberate gap here, because the only thing this leading coefficient test tells you about is what happens on the left and right ends of the graph. We're going to get some other information as to what happens in the middle here shortly. But positive lead coefficient on even degree, the left and right ends go up. If you have an odd degree with a positive lead coefficient, the left and right ends go in opposite ways. The left end will always go to minus infinity, the right end goes to positive infinity. So here's an example of a degree 3, an odd degree polynomial that has a positive lead coefficient. The left end goes to minus infinity, the right end goes to positive infinity. And then when you change the sign of the coefficient, it naturally flips these end behaviors. An even degree with a negative lead coefficient, left and right ends will go down. An odd degree with a negative lead coefficient, the left end goes up, the right end goes down. So this is an example of degree even, degree 4, that has a negative lead coefficient because the left and right ends go down. Here's a degree 5 that's odd, and the left end goes up like this, the right end goes down like this. So that's an example of one that would have a negative lead coefficient for odd degree as well. So putting the leading coefficient test into practice, let's just determine the end behaviors for these polynomial graphs. In other words, just based on their degree and the sign of the lead coefficient, what are the extreme ends of the graph going to look like? Okay, just giving you a rough idea of what the sketch would be. Here's an example of odd degree with a negative lead. A negative lead coefficient. So, odd degree with a negative lead coefficient, without even looking at the calculator's graph, without even needing the calculator, that much information guarantees that the ends are going to look like this. The left end is going to go up, the right end is going to go down, and again, we can't discern anything about the middle behavior just yet. We'll learn that later, here in a little bit. But that's what the leading coefficient test guarantees would be the end behavior for this graph. Now, when it's in factored form, you actually don't have to factor to FOIL all this back together. You can leave it in factored form and still get the degree and the sign of the lead coefficient. If you were to multiply all these highest x values together, all the highest x's in each factor would contribute to the highest power of x as well as your lead coefficient. So if I multiply all those highest x's together, I've got 1x squared times 3x times x. If this were to multiply out, that would give me 3x to the 4th as the lead term. So you don't even need to know the lower terms because the leading coefficient test only applies to the highest power of x and its coefficient. So if this were all FOILed out, your first term would be this. Now you'd have a few other terms, but those aren't what we're focusing on right now. So notice you have an even degree that guarantees that the ends are either going to go both up or both down. But then with a positive lead coefficient, then that means that this graph is going to have end behavior that looks like this. Even degree with a positive lead, the left end and the right ends are going to go up. And we'll discern information about what happens in the middle here shortly once we start talking about the zeros of a polynomial.